All right, so we have a nice review problem here. Let's see if you guys can remember. Why don't you go ahead and try to do this review problem and push pause, and when you're done, we'll go over it together, okay?
All right.
Okay, did you get to try it?
Yeah, I did it.
Okay. So, how many liters of nitrogen at 1 atmosphere and 0 degrees Celsius are prepared by the decomposition of 150 grams of sodium nitrite?
Well, you got to use dimensional analysis.
That's right. We have to go 150 grams of NaN3.
And then you got to relate that to liters of nitrogen.
Very good, liters of nitrogen. How do I do that?
Well, you take the molar mass of sodium nitrite.
That's right, grams of sodium nitrite, NaN3, go to moles of NaN3. Why do I always want to go to moles?
So you can get the power of the equation.
That's right. After I know how many moles of sodium nitrite I have, then I can relate the moles of sodium nitrite, NaN3, to, this is moles, to moles of nitrogen. And for every mole of nitrogen that I have, I can identify how many liters of nitrogen. In fact, I think it's going to be easier for me to just stop at moles. And then once I stop at moles, I can use my understanding of standard temperature and pressure, right? Which is, these are the conditions that they're talking about, 1 atmosphere at 0 degrees Celsius, and know that my volume is going to be 22.4 liters, 22.4 liters for every mole of gas.
Where did you get that?
Well, a while back we said that all gases have the same volume at the same temperature and pressure, and that at standard temperature and pressure, which was 1 atmosphere, 0 degrees Celsius, the volume was 22.4 liters. So in fact, it's probably, if we get to use that, then we can go from moles to liters, saying that there are 22.4 liters of gas for every 1 mole of that gas. All right. Our stoichiometry shows that it's 2 to 3 here, so 3 moles up there. Do you know the chemical or the molar mass of what's it called? Sodium nitrite is?
I don't.
It's 65 grams per mole. All right, so here we have our resulting volume. Again, if we work through this, 77.5 liters of nitrogen gas, because every mole of gas at STP has 22.4 liters. Okay, according to the following gas phase reaction, what volume of C would be required to react completely with 23 liters of B?
I don't know how to answer that question.
Well, if I had said 23 moles of B, how many moles of C would we need? Could you do that?
Yeah, I could do that.
Well, that's essentially what we're doing. We're using the stoichiometry, but now we're relating stoichiometry in terms of liters, and we can do that because they said that this is a gas phase reaction. All of our reactants and products are in the gas phase. So, unit analysis, dimensional analysis here, looking at for liters of C, right? Starting with 23 liters of B. And for every, what's the relationship between liters of C and liters of B?
5 liters of B for every 3 liters of C.
That's right. 5 liters of B for every 3 liters of C. So if we had 23 liters of B, 23 times 3 divided by 5 would tell us how many liters of C we would need. Okay, good. Now, we don't have the right units to create what we call, a single statement that says, if you tell me how many liters of a gas you have, and the temperature of that gas, and the volume, I should be able to tell you the pressure of the gas, right? The problem is all the units are different from each other. And so we have something that's called the ideal gas law that brings together all of our different parameters into one statement, where we have pressure and volume being related to the moles and the temperature. All right? So if I know the pressure and I know the volume and I know the moles of material, I can tell you what the temperature is. Or if I have any three of these, I can tell you the fourth. All right? And actually have an equal sign in here as opposed to just a directionally proportional symbol, right? Using a correction or a conversion, right, a constant, and the constant will have the appropriate units. Now, these units can be different for different pressures, because you can have pressures in terms of liters or milliliters. You can have volume in terms of, pressure. Volume instead of liters or milliliters. Pressure in terms of atmosphere, torr, or temperature. Temperature is always going to be Kelvin, and moles of gas is always going to be moles. But because of the possible differences here, your R value could be different. And when you go and search for the R value, because you'll forget, was it 0.07 or 0.81 or what was it? When you go to search for it, you have to make sure you get the one that has the correct units, so that whatever units you're dealing with, or whatever pressure or volume units you're dealing with, they'll match the units here. Or conversely, you can get whatever ideal gas law you find and then make sure your units are adjusted. So this ideal gas law we call PVNRT, P-V-N-R-T, and that becomes familiar to us after we say it multiple times. And again, we have to kind of pay attention to our units to see how it relates to the units of whatever R value we are using. Okay, so here's an example. If I have 0.22 grams of a sample of neon, and it's in 5 liters, and the flask is at 25 degrees Celsius, I should be able to identify what the pressure of the gas is. Okay? I don't know how many moles, but I do know that I have 12.2 grams, so I can convert that to moles by dividing by 10. 20. Neon has a mass of 20. So 12.2 divided by 20, that gives us our moles, 0.61 moles. That's how many moles of neon I have. The temperature, 258, it has to be in Kelvin. So 273 plus 258, that's 298 Kelvin. My R value, 0.0821. That is liter atmospheres per mole Kelvin. If you look at those units, that'll work, because moles will be canceled out, Kelvin will be canceled out. I'll be left with liter atmospheres, and then I have liters and atmospheres over here. I don't know the pressure, that's what I'm after, but I know the volume, and the volume is in liters already, so I have 5 here. So now I can just use my calculator to solve for the pressure. My moles, 0.61 times 0.0821 times 298, and that will give me 14.9 14.9. Did I do that right? 0.0821, 0.61, 298. 0.0821, that's right there. 3 atmospheres. What did I do wrong there? 0.61 times 0.0821 times 298 divided by 5, and that should be 2.98, so 3 atmospheres. All right, excellent. Now, density of a gas. Density of solutions, we were expressing them usually in terms of grams per milliliter, but for gases, we express them in grams per liter because they have a much smaller density. And so expressing them in grams per milliliter is just a really small number. Grams and liter is a reasonably sized number. Okay? So we can change the moles of our material into, in our ideal gas law, PV equals nRT. We can change the units of N to grams over grams per mole, or grams over the molar mass. And now, why would we do that? Well, we can then rearrange the volume over, bring the volume over here, and it leaves behind the grams over the volume, and that would be our density. So we can rearrange things and get the P times the molar mass to equal the density of the gas here times RT. Now we're not going to go over any problems like that, but for density necessarily, but you can see how this insertment of grams over molar mass for moles, right? So let's look at that. Moles equals grams over grams per mole, right? If I take grams over grams per mole, that's the same as multiplying grams times moles over grams. Grams cancel out and I get moles, right? Okay, very good. So what is the what we do want to use this equation for is to find the molar mass of a gas. So in this scenario here, we can say what is the molar mass of a gas which has the density of 6.7 at negative 73 degrees Celsius and at a pressure of 36.7 psi. Psi is another expression of pressure. So what's the molar mass? Well, I know PV equals nRT, and I know that N, being moles, can be replaced with grams over grams per mole, and that grams per mole there is the molar mass. PV equals grams over grams per mole, RT. And I want to find the molar mass by itself. I can bring the molar mass up here. Now I'll write it as just molar mass times the pressure and the volume equals the grams of material times the gas constant times the temperature. All right, so the density of our gas is 6.7 grams per liter. I can take this grams and bring the volume down here, right? Divide both sides by volume. And then that right there will be the density of our gas. So 6.7 can go right there. R 0.0821. This is in grams per liter. That's fine. Temperature negative 73 plus 273 Kelvin is going to give us 200 degrees Kelvin. All right. Now, to get molar mass all by itself, I just need to divide by pressure there, and the pressure is 36.7. I'm just going to go to the, let's see, I'm going to go to the internet here and ask the internet what how many atmospheres are in 36.7, whoops.
Here's a matching video.
How many atmospheres are in 36.7 psi? So that's
36.7 pounds force per square inch is equivalent to 2.497 standard atmospheres.
So
to
that's,
convert from pounds force per square inch to standard atmospheres, divide unit of pressure by 14.7.
got it. All right, so that's 2.5. So now we go 6.7 times 0.0821 times 200 divided by 2.5, 44, and that is in units of grams per mole, and so that is the molar mass. All right. So this is a way to identify the actual molar mass of a compound, which we really haven't had an explanation of how this would be done in the past, right? But we see that we have the ability, and we're not going to probably do this much in any of our questions, but it is an interesting expression to see that if you know the pressure of, so here's a balloon. I don't need to know, so here's a balloon, and the pressure on all balloons, if they're, in your house or on the beach or wherever, is basically the same. It's always 1 atmosphere. So if I have a balloon full of a gas, and I can tear the balloon, that means, weigh it on a balance before it's full and then after it's full, then you can know the mass of the gas, right? And if I can submerge this into water, I could know, well,
here's a
that
matching
probably won't be
video.
the best way to do it because then it would change this pressure, but I could measure the outside of it and find out the volume.
36.7 pounds force per square inch is equivalent to 2.497 standard atmospheres.
I can relate
to convert from
pressure,
pounds
1
force per
atmosphere,
square inch to standard atmospheres, divide
density,
unit of pressure by
grams per liter,
14.7.
and the temperature to the mass, the molar mass of the compound inside. All right? So it's a way to identify the molar mass of a compound, a gaseous compound, if you have all the different known parameters associated with it. Okay, good. Good place to stop.